This topic was a fairly big deal in Computer Science 20, but I'm only going to devote a few minutes to the issue of predicates. So far we've talked about propositions. I denote one now by capital P instead of little p, but it's like a Boolean variable. It's something that's either true or false. A predicate, in contrast, is a function, and we write it p of x. It's a function of an integer x, and it may be true for some values of x and false for others. A simple example of a predicate is being a prime number. That would mean that p of 2 and p of 3 are true because 2 and 3 are prime numbers, p of 4 is false, and so on. Just as functions can have more than one argument in general, so predicates can also have more than one argument. An example might be a predicate named enrolled, which is a function of x and y, where x is a student, y is a course, and this is true if the student x is enrolled in the course y. When you're talking about predicates, it's important to specify the domain of the function. And in this context, that's usually called the domain of discourse. In the previous example, I might, for example, be more specific and say, I'm considering the set of Harvard courses and the set of Harvard students. And then we all know what we're talking about. Quantifiers you have almost certainly seen before. If you took Math23A, this was very nearly the first topic, and you're familiar with the existential quantifier. If I say there exists an x such that p of x is true, or drop the such that, which is generally understood, and write just there exists p of x, what that means is in the domain of discourse there exists at least one x, there may be more, for which p of x is true. The other quantifier we need is the universal quantifier for all. And when I say for all x p of x, what I mean is that for every x in the domain of discourse, p of x is a true proposition. You're very likely already familiar with the rules for negation of propositions that have quantifiers in them. The first rule is that the negation of the existential quantifier involves the universal quantifier. The negation of the statement, there exists an x for which p of x is true, is for all x, p of x is false. And these are two equivalent statements. You can always trade one of them in for another. The negation of the universal quantifier involves the existential quantifier. If I want to show that the statement p of x is true for all x is false, all I have to do is exhibit one x for which p of x has the value false. Now, we can easily have multiple quantifiers. Let me preface that by pointing out that statement, there exists an x for which p of x is true, is not a predicate, it's just a proposition. It's either true or it's false. And If I have a predicate with 2 arguments and apply one quantifier, the statement, there exists an x for which p of x and y is true, is a function of y. So that's a predicate which I could write in the form q of y as a function of y only. If I have a predicate with 2 arguments, I can precede it by 2 quantifiers, and this means there exists a pair of values, x and y, for which p of x and y is true. The order in which I specify x and y is completely irrelevant here. That's also the case if I say for all x and for all y, p of x and y is true. However, when I mix the 2 kinds of quantifiers, it makes a big difference. If I say there exists an x with the property that p of x and y is true for that x and all y, that's a different statement than the statement for all y there exists a single x for which p of x and y is true. A standard example of this distinction is the distinction between a continuous function and a uniformly continuous function. So watch out in general. If you have the 2 different types of quantifiers, the order is important. Now think back to plane geometry. The usual statement of Euclid's 5th postulate is, given a line and a point not on that line, there exists a unique line, including that point that's parallel to the given line. So that's probably the earliest well-known example of exists and is unique. Let's try writing this using quantifiers. We want to say there exists one and only one value of x for which p of x is true. I warn you, this is quite a bit harder than it looks. Here's my first attempt. I say there exists an x for which p of x is true, and for all y, p of y is false, but p of y is not false if y equals x. So what I have to say instead, there exists for every y, if y is different from x, then p of y is false. That's okay, but it's extremely clumsy. Let's simplify this by using our knowledge of the fact that p implies q is the same thing as not p or q. So I change y different from x to y equals x. I change implies to or, and I now have the statement, there exists an x for which p of x is true, and for all y, either y equals x or p of y is false. That's pretty good, but we can do better yet. How about this? There exists an x with the property that for all y, p of y has the same truth value as y equals x. In other words, p of y is true if and only if y equals x. And this is probably the best way in general of expressing exists and is unique. Of course, if you're willing to introduce new notation, you can introduce a symbol exists exclamation point, and this means there exists a unique x for which p of x is true. Let's finish up this brief topic by using predicates to convert English sentences into statements of predicate logic. And I think this example came straight from Computer Science 20. We're going to let h of x means x is happy, and let L x comma y means that x loves y. And now we're going to try to write some statements involving happiness and love. Easy start. At least one person is happy. There exists an x for which h of x is true. At least two people are happy. There exists an x and there exists a y for which h of x is true and h of y is true, and here's what you're likely to overlook: x is different from y. At least one person is unhappy. That's easy. There exists an x for which h of x is false. Exactly one person is happy. Well, you saw this on the last slide. There exists an x with the property that for all y, y is happy if and only if y is equal to x. Now let's try not everyone loves someone else. There are several different ways of writing this. I'll work through it. We spent about half an hour the year I taught CS20 working on the old Sara Lee jingle. Everyone doesn't like something, but nobody doesn't like Sara Lee. And finally concluded that this was so ambiguous we couldn't agree on how to write it in predicate logic. But let's tackle this one. Here's a rather mechanical way of approaching it. Let's write everyone loves someone else and then put a not in front of it. So everyone, for all x, loves someone. There exists a y for which x loves y. Someone else, that y whom x loves is not x. So that's correct. Now let's apply the negation rule for the quantifier. I have to change the quantifier from for all to exists and slip the negation inside. So this is another way of writing it. There exists an x with the property that there is no y for which y is different from x and x loves y. I'm not sure that's an improvement, but it's at least a good intermediate step. Let's apply the rule again. Okay, we'll slip this inside the quantifier, and that means the quantifier turns into the universal quantifier. So we now say there exists an x with the property that for all y, it is not the case that y is different from x and x loves y. One last one. We know De Morgan's law. If you have not of an and, you can change the and to an or and negate both propositions. And I think this is probably the best way of expressing not everyone loves someone else. There exists an x with the property that for all y, either y is equal to x or x does not love y. And with that, we will end our discussion of predicates and move on to a completely different topic.